For the first part of the research day, we go to PIs in the FIU, starting with Amer Awwad, who is going to present development of rapid in-situ testing for concrete deck durability. Amer?
All right. Good morning, everybody. I'll be presenting the project with my co-PI, Dr. Kingsley Lau. And our project is development of rapid in-situ testing for concrete deck. Little background. Steel is used in reinforced, pre-stressed, and post-tension concrete structures to resist tensile forces. Deterioration of reinforced concrete in severe environments due to chlorides, sulfates, frost, and others result in loss of structural capacity. Chloride-induced corrosion of steel and concrete is of interest to structures exposed to de-icing salts and marine environments. A little background. A method to quickly assess the durability of hardened concrete material against liquid ingress has been developed at FIU. The aim of this project is to establish a relationship that might exist between the method developed at FIU and the standard test methods, including freeze-thaw, rapid chloride permeability, bulk resistivity, and surface resistivity. If such relation exists, the durability assessment of concrete bridge elements can be achieved in less than 20 minutes with the FIU method. The FIU testing apparatus consists of the hydraulic pump, you can see over here, the pressure transducer, the data acquisition system, and the test specimen holder. The testing in this configuration is set up for a cylinder, but this can also be used for flat surfaces such as pillars and other concrete surfaces. The apparatus is capable of testing the concrete specimen's resistance to water penetration. The specimen holder consists of two 1.5-inch steel flanges. You see one on the top, one on the bottom, and there's an EPDM gasket between the top and the concrete specimen. The concrete specimen is held between the two flanges by 4 steel bolts. The T on the top has the pressure hose connected on one end, and on the other end we have the pressure gauge and a purge valve. The purge valve is to purge all the air that might be in the line before we start the test. Previous testing, we tested 2 types of concrete. One is the UHBC, you see over here on the left, and also regular concrete. Both specimens were pressurized at 200 psi, and then the isolation valves were closed, and that left the specimens pressurized with the 200 psi water, and then we monitored how the pressure dropped over 20 minutes. And the results, you can see the red and the blue line over here are the UHBC, while the brown and the gold color are the regular concrete. As you can see, there's about 100 psi drop with the regular concrete, while there was very little drop at the UHBC. The current testing we've done is we use a concrete mix equivalent to an M20. The specimen water content was varied between 0.5 and 0.6. They were kept at different moisture contents between dry, 75%, 95% relative humidity, and also soaked. Also, the aggregate size was we had 2 different aggregate sizes, a 5.7 and an 8.9. The aggregate was limestone, and we made 2x4 and 4x8 test cylinders. The concrete cylinders were conditioned with the moisture content. One of them was one set was dry, which was left below 35% relative humidity. And then we had, as previously mentioned, 75 and 95 relative humidity using sodium chloride and potassium sulfate. Then there's an immersed, which was a soaked in calcium hydroxide solution. The mass change and bulk resistivity were monitored over time, as you can see over here on the right. This is the results of the first set we did. There's 4 specimens that were tested for each of the different moisture content between wet, 95, 75, and dry. The dry is the green, and you can see that had the greatest pressure drop. Then 75 is the brown color. Then between 95 and red, they are sort of intermingled between here. So very little difference between them. So as the drier the specimen are, the more pressure drop we're getting. This is a more detailed look of each test based on the rock size. On the left, we have the wet with the 5.7 rock, and on the right, we have the 8.9 rock. The blue line is the 0.5 water cement ratio, and the brown line is the 0.6 water cement ratio. As you can see, the 5.7 at the wet condition, both the water cement ratios are on top of each other, while the 8.9 there is some separation. When we go to the 90%, we have there's some separation with the 5.7 rock, and the separation on the 8.9 is getting closer to each other. We get to the 75, there's more separation on the 5.7, the 8.9 is getting even closer. The 5.7 dry has the greatest separation, while the 8.9 dry is very close to each other. And now I'd like to have Dr. Lau to present the next stage.
And so since the concrete core samples were conditioned in those various moisture environments, we also tested different concrete parameters, including electrical parameters and acoustic testing. And the idea for this type of testing is to try to gauge and correlate some of the measures we get from the water pressure drop onto some of these other parameters. And so we did some electrical testing, including electrochemical and penis spectroscopy. And so the idea with EIS, we can identify the characteristics of concrete, including development of a resistive path and capacitive path that describes the solid parts of the microstructure of the concrete, as well as any moisture that's available in the system. So we have 2 fairly busy graphs on the right-hand side, the top one being the resistivity result from the EIS measurements, and we have our different rock size, limestone 5, 7, 8, 9, broken down to the water cement ratio and environmental content, and the same thing as well as the concrete capacitance, also broken down by the aggregate type, water cement ratio, and the moisture condition. So by observation, we can see that when the concrete is wet, we can see that the wet resistivity corresponds to expected behavior, where we have the lower quality concrete with the higher moisture content have a lower wet resistivity, and that's for all cases with the rock. The capacitance shows similar behavior in the wet condition. Ideally, we'll see a higher capacitance that's related to the higher capacity of water, for example. The dielectric of water is much higher than that of the aggregate or the cement itself, so that's to be expected. But interestingly enough, when we plot them together, if you see in this graph here, we'll correlate the capacitance of the concrete to resistivity of the concrete materials. We start seeing separation of the data between the different water cement ratios and rock type. So the blue colors represent the 0.6 water cement ratio, and the orange represents the 0.5 water cement ratio. Solid lines represents the 5.7 rock, and the dashed line represents the 8.9 rock. And so we see separation of materials. So we see when we have a lower resistivity, high capacitance, we have the concretes where we have poor quality concrete with higher moisture content, and on the bottom right-hand side, greater resistivity and lower capacitance for the other concretes. So with this data, we're seeing some separation materials, and hopefully we can get this correlation with the rapid water pressure drop samples as well. We also measured the longitudinal resonant frequencies of the samples at the same time. Again, and these graphs over here, we have the longitudinal resonant frequencies with the rock type, the water cement ratio, and the moisture content. And we have to resolve modular elasticity to get from the resonant frequency. So we have 2 y-axes. One is for the 4-inch samples, one is for 2-inch samples. They correlate well with one another. And similarly, again, when we plot them in terms of the modules to resistivity, modules to capacitance, we again see some differentiation between the water cement ratio and the rock type. Again, the 0.6 being blue, 0.5 water cement ratio being orange, and the dashed line being the 8-9 rock, and the solid lines being the 5-7 rock. So we're seeing some separation. Again, ideally, we can correlate this to water pressure drop with the testing that we have at hand. And so here's another example of how the testing was done, as Amer was explaining. So this is from one of the test samples. Again, we see the dry concrete, we have this much greater extent of water pressure drop compared to the cases when water already exists. And so one metric to do this is actually to measure a delta in pressure between the initial time and 20 minutes, for example. This 20 minutes was chosen fairly arbitrarily, but we see that there can be consistency as long as the test was made similarly. But we also try to fit these graphs. We see that they follow an exponential decay, and we can get a term that describes the whole entire line. So it resolves some of the discrepancies you may get by having differences in the early initial pressures and the timing that you choose for the timing of the pressure drop. So here's a graph showing again pressure drop to the different concrete types with the different outsized aggregates and water cement ratio and different moisture conditions. So the gray lines represent the pressure drop measured in 20 minutes, and the white bars represent the decay factor, which I'm going to describe next. So the decay factor really is trying to describe the signature of that decay line. And so when we correlate the pressure drop to the pressure decay factor, we see that they correlate very, very well. So I guess, how do we get this decay factor? So we try to model this in terms of a mass balance and energy balance system. So the first case considered when we have a pressure vessel, the water held at 200 psi, for example, and we first assume that the concrete pores have low pressure and the water can freely flow through these pore systems, an apparent pore system. When we solve this problem, again, with mass balance and energy balance, we get an equation, but unfortunately the fit wasn't great. And so the curves that we see, that the decay actually is a factor of time. So it seems like the pore sizes are changed with time, which makes sense because the pores are essentially getting saturated with water with time. So we modify this equation to have a term where we look at what I call a pore saturation factor. So that is, how much does that pore gain wet with time? So we include this exponential drop of time, saying that the area of pores, whatever may result to be, it will get smaller and smaller time as the pores saturate. We can solve this equation, differential equation, again with energy and mass balance, and we see the fit data, the blue line, starts to fit very, very well with the actual data points. And so this decay factor K is what we're getting here for our graphs, and we think it's a good way to characterize these curves. And what we're seeing is very interesting to us is that the dimensions for this K factor relates to the pore size and the pore saturation, which we would like to try to identify conditions of the concrete and characterize the concrete. So here's a graph showing a little bit of correlation we're seeing. Again, the K factor, at K factor, we get characterizing that pressure drop, and we plot it versus resistivity, for example. And wet resistivity is a common metric we use to identify durability for concrete. And we see that the resistivity and decay factor K for a water pressure drop correspond very, very nicely and very well. And what we tend to do, what we want to do is get a K factor again, try to ascribe that factor to the apparent pore size and pore size distribution. Likewise, for other electrical conditions, capacitance also shows good correlation with the K factor. And so we also conducted other tests that we want to correlate with the water pressure test. We conducted the freestyle test. And so we had the same samples cast at the same time, made into prisms, and we ran the ASTM C666. You see a picture of it inside the chamber during testing or after testing, and also looking at the longitudinal resonant frequency sample afterwards. This is an example of the concrete prism after freestyle testing. You can see the damage due to frost. And so here are some curves that we got to try to correlate some of our test conditions, hopefully to resolve how well the pressure water pressure drop corresponds to other type of testing. So on the left-hand graph, we have our electrical testing, resistivity and capacitance correlating to this relative dynamic modulus. this relative dynamic modulus is actually saying how much of the strength of the concrete is lost after the freeze thaw, accelerated freeze thaw testing. So the higher number, the more resilience it has to its attack. So at least for electrical testing, we can look at the blue lines. The blue lines represent conditions where the concrete was soaked, so the pores were saturated. And we see that the better performing concretes with a higher relative dynamic modulus are those samples with a higher resistivity and those with a lower capacitance. So this represents those concretes that have a higher cement factor, and so the higher quality concrete. So they'll give you better behavior, and the wet condition it helps us to give us better control of the test samples. On the other hand, we also correlate our frost freeze thaw attack, the relative dynamic modulus, to that pressure decay factor that we're talking about. And first condition, we can pay attention more to the dry conditions, where the samples were in dry conditions. Again, to try to control the initial setup during testing. And we can see that we have better frost freeze thaw resilience for samples when we have a larger pressure decay factor. And this we're ascribing to those samples that have a larger air content. So the larger air content, airspace, the more air volume that the water can have when it freezes, and then thus have less damage. So we're continuing to work on this to better resolve the individual concrete components, including its water cement ratio and rock type and so forth. Our next step, we're also looking at the RCPT test. We have samples ready, and this is ongoing, and we'll have those results shortly once they're completed.
Okay, the next phase of the testing we'd like to do is change the aggregate from limestone to river rock and to granite. Again, sticking to the 8, 9, and 5/7 size. We would like to do the next is do a field application demonstration instead of just doing it on cylinders, do it on actual concrete specimens with bigger size. And what we're going to also do to check do the testing with various compressive strengths of the material and environmental conditions, and see how they compare with the different phases of we did before. The water pressure test will be made to demonstrate an application to cast concrete slabs in various thicknesses. Deliverables, a final report summarizing the experimental results, complete system design of the FIU system, ABC UTC guide, and a video presentation will be prepared that summarizes the methods used and the findings reached during the project. Some research highlights. Testing shows differentiation between pressure drop to the concrete properties and conditioning. Developed a model to identify the concrete mix designs and internal moisture content, and developing a correlation between novel water pressure tests and the existing durability testing. This is our research team, and that's it. Any questions?
Thank you very much, Amer and Dr. Lau. We have a couple of questions, and I think we have good time to see if we can answer these questions. One asking what kind of surface preparation you will need so that you don't have bias or error in your measurements.
Yeah, so that's true, and especially in field concrete that has been exposed for a long time, there can be differentiation on the surface. One concept is carbonation. We're talking about that in some of our other work, and so there's always going to be a near surface that's carbonated, and the concrete properties are a little bit different at that skin. So even when we do other on-site field testing, that's always been a problem. So what some field practitioners do is actually try to roughen that surface to remove that skin. Like even for example, surface rigidity, that skin on the outside of concrete will have a difference. And so one could come with an abrasive grinder, for example, and just to remove that very, very thin layer on the surface to do some measurements. So conceivably that can be done on here as well. In terms of moisture content, we are seeing that there is different behavior when the concrete is wet or when it's dry. Both show different things, but very interesting. You can try to get difference in the concrete material itself. So we're thinking when we start doing some trials in the field is to evaluate the systems when it's wet and when it's dry. And so that can be done in practical sense too. In a dry sense, basically getting some type of heater on the surface or different ways we're talking about. Amer has some ideas of even using pressure, that type of thing, to remove that water. So you can dry the concrete, run this test, and see how the water penetrates. Likewise, you can wet the surface and just ponding it and have it initially wet on the air surface and also run a test. And with future testing, we're hoping really to use those to gauge, really to get a sense of what the concrete material is like. Any other comments? I think for the most part, for field cases, I agree. Yeah, you can roughen the surface to remove that skin to resolve some of the issues of carbonation, and the moisture content we feel can be controlled as well.
Yes, the other thing is that the surface needs to be fairly smooth because of the gasket. We need to seal it, so it would have to be maybe ground down to a fairly level surface so that we can get a good seal between the system and the concrete.
I think, Amer, that's probably is the what you just mentioned, because sometimes the what they call the mortar or the cement comes and collects on the surface and creates a false like a smooth surface or so. What you mentioned as grinding, and probably, and Dr. Lau mentioned, probably is a good way. So to just make everything uniform or so. Dr. Lau, you mentioned the moisture. There's a question asking, is it like, do you need to know the moisture content in the concrete so that you can conclude the permeability or something? Or what, as I think you just mentioned, maybe dry before testing. So what would be, I saw some curves in there that would probably you could use with that K factor to see how what the moisture level is. So what would be the procedure? Knowing the moisture or determining the moisture?
So both. So the initial phase of this research was initially to understand what is the role of the moisture content, because our feeling was that it will affect the measurements and how to interpret it. So in testing, we want to control the moisture content just to understand. But fortunately, with the data, we're seeing that due to testing whether it's dry or what is wet, they have different behavior, which can help us resolve that K factor, which dimensionally is correlated to the initial pore size and how much those pores can be wet. So we're thinking we can attribute to the pore distribution as well. And so knowing the moisture content, I think that you can determine important parameters such as porosity of concrete, for example. We're stretching a little bit, but we're trying to get there. It's the pore sizes, air space, and also the distribution of the pore sizes. But in a more practical sense, if you're not going to be able to know that in situ, we feel that we can control the concrete in the field by drying the concrete or wetting the concrete and doing the same type of test we did in the laboratory, really to get different ways to gauge the concrete. So the stuff that we're working on, trying to refine it a little better. We're hoping that this testing will give us a good way to describe multiple characteristics of concrete, including its durability, its permeability, moisture content, porosity. And we think the data can get there, as well as we can calibrate the data and try to refine its effect on that pressure drop.
I say that would be great, because it will completely close the loop. Won't leave anything unknown. There are more questions, but I have to stop it right here. Thank you very much, Dr. Lau. Thank you, Amer, for good presentation. That's excellent project.